Okay, I think it's recording.
Yep, the floor is
Okay.
yours.
Hello, everyone. Good afternoon or good morning, wherever you are. Uh, so my name is Alexandros Krekos. I'm a third-year PhD student at Stony Brook University, and I will be presenting our work on diffusion models as plug-and-play priors, which we actually also presented at NeurIPS 2022. And this was in collaboration with our friends over at Mila, Nikolai, and Microsoft Research in Voja, whom we've been working with for a varied number of topics, but diffusion models as well. So I think I'll just start, and I'll just start by describing the overall setting and what the idea was initially. So very briefly, what Gaussian diffusion models are. I'm pretty sure that everyone is familiar by now, but they're a new type of generative models, or was a new type of generative models, where you basically learn to reverse some corruption process. And for Gaussian case, this corruption process is adding Gaussian noise. So they define two processes, the forward and the backward process, or reverse process. And in the forward process, you start from the data, and you define a Markov chain that gradually adds noise to the data and basically corrupts it. And what you have to do is that you have to learn the reverse process, which, starting from the tractable Gaussian distribution, you want to basically undo all the corruption steps so you can draw samples from your data distribution. And basically, to do that, you will learn neural network approximation to this reverse process, which defines implicitly a marginal distribution over the samples x0 images in this case. But the important thing here is that you do not have this explicit distribution. You just end up with a denoising network. So the question we wanted to ask was, how can we use this denoiser network that we end up with after training the Gaussian diffusion model to basically do any other task where we can use this as a prior distribution? And so in general, the way you would train these models is that you approximate every denoising step with this network. And the objective that people have introduced and have been trying to optimize and doing variations of is basically that you learn a denoiser or a neural network approximation to remove the noise at every noise level. So in general, you have a large number of noise levels, and you will train your network to be conditioned on the noisy sample and the time step, and you'll try to remove this noise. But the important thing here is that you only end up with this network. You don't actually have a way of knowing what the distribution that you learned is. You only have the denoiser network. And this is what this process looks like, basically. So you will have your images, you will be adding noise, and you will just learn to do the denoising steps. Now, we know that after you've trained this Gaussian diffusion model, you can draw very diverse and high-quality samples from the underlying distribution. And in this case, I'm just showing examples of human faces and churches and cats and bedrooms. But people have shown that these are much better samples than what you would get with a GAN. So ideally, what we would want to do is to use this trained model with any auxiliary constraint that we can think of, and draw samples that will both satisfy this prior distribution that the model has learned, but also the constraints that we impose upon this model. And these constraints, we call them C of X and Y. It can be pretty much anything that we can think of, and I'll show a few examples of the applications that we came up with. And in general, we call this a plug-and-play combination of the diffusion model and the classifier or whatever else you may have. But the plug-and-play term we figured out is a bit, I don't know, people didn't like it as much because it's a term also in inverse problems. So there's previous work on this. This is not a new idea. People have been doing this with GANs. This is a paper that by Benjo, who basically did the same thing with GANs, where there you wanted to use your GAN with some other classifier to generate samples. But people also have been doing this for inverse problems, where, for example, medical imaging, you have some very well-defined linear inverse problems, and you can solve these problems by using these score-based priors or diffusion models or whatever. So the plug-and-play term, I want to clarify this because this was a bit contentious with the reviewers as well. We're just referring to it as being able to use this diffusion model as a prior and use it with any other kind of constraint that you want. It's not defined in like terms of linear inverse problems or any sort of category that plug-and-play has also been used in. So how we're able to do this is that, let's say we have this conditioning y, and we want to approximate the posterior of x given y. And this posterior will probably, you're all familiar with, we will say that this is proportional to p of x times this constraint that we have, which is p of y given x in most cases. And we will use a variational posterior, q of x, which we will try to fit by minimizing the negative elbow or the free energy. Now, this is a standard procedure that we would do in any other case. But the difference here is that this p of x term is now our diffusion model, the trained diffusion model. And so we need to come up with a few smart ideas to basically use this diffusion model in a way that we can parameterize it with the tools that we have, which is basically the denoiser network. So what we found is that if we just constrain ourselves to seek a mode of this posterior distribution, which means that this variational posterior q of x will just be a delta function, then one very nice thing that we can get is that we can tractably sample the xt at any time step, which is very important for these diffusion models. So this is what we would get, the intermediate steps of this denoising process. Basically, we would just use this is a point estimate, so we just use the point that we have at the current step, and we can sample at an intermediate time step. And this is also very important because what you also need to have to be able to use these diffusion models is that you need to be able to have a tractable, have this conditional Gaussian be tractable, which is q of x t minus 1 given xt and x0, which in our case is our point estimate eta. And by being able to have this as a tractable distribution, then we can express this first part of the expectation as a sum of KL divergence terms. And this is the same thing that they do in the original diffusion paper. But here we're just saying that if you set your variational posterior to be a delta function or a Gaussian, which would be equivalent for our derivation, then you can use whatever they used in their paper to be able to also express this first expectation in the elbow as a sum of KL divergence terms, which is very important so that we're able to actually estimate the negative elbow. So if
can I ask a
yeah,
question? Sorry.
Sure. Yeah.
Why do you choose to put the posterior as a delta? Actually, that's not clear to me.
So if by choosing the posterior as a delta, then we both get the tractable sampling at every time step, but we also get we're also able to express this conditional Gaussian distribution tractably. So in order to be able to, we want basically to split this negative elbow into two terms. I'll show it in the next slide. But the first term, we want it to be the term corresponding to the diffusion prior. And the second term will be corresponding to the conditioning. So in order to be able to split it into two terms, we'll need to have the first one as a sum of KL divergence terms, which is the same thing they do in the original DDPM paper. So to be able to do that, you need to have this tractable and also be able to sample xt at every time step.
But you mentioned that you can do it also with a Gaussian, right? With a Gaussian posterior.
Yes, with a Gaussian posterior, you can do it as well.
Okay, so why would you then use the delta rather than the Gaussian?
I'll show that even with a delta, you're not constrained to just sampling a single mode because there's a lot of things that happen. There's a lot of stochasticity and so on. So it's a much simpler approximation, and we get variety in the samples, and we get everything that we want out of it.
Okay.
But it's basically the simplest thing we can come up with.
Okay, thanks.
So yeah, by using a delta, we're able to basically write this expectation as a sum of KL divergence terms. which if you read the original DPM paper, this is the same thing that they do, and they do all the derivations to show that if you are able to write this as a sum of scale divergence terms, then what it ends up is you can also write it as a sum of these denoising terms. Basically, what we show is that instead of minimizing that very complex negative elbow, we can, by assuming that this is a delta, the variational posterior is a delta, we can basically express it in these very two simple terms. The first one is corresponding to diffusion prior, and basically just tells us that our xt, which is the intermediate time steps which we can easily sample with the delta approximation, we need to be able to denoise these terms, to be able to denoise this approximation basically at every time step, and also be able to satisfy the conditioning, which is much simply, it is a very simple way of thinking about it. So the conditioning is just log likelihood, basically, of whatever we have. And the diffusion prior is basically the fitness of our estimate, of our current estimate, to the denoiser. So although we're sampling from a posterior distribution, the biggest difference is that we're no longer using the sampling algorithm of the diffusion model. So basically, our algorithm is an optimization procedure where we start with some initial estimate of what the final image, for instance, looks like. And we perform a lot of optimization steps and try to fit it such that it satisfies both the diffusion prior, in the sense that the diffusion model can easily denoise it, and also the condition that we set upon it, which can be any condition. And also, yeah, it can be generalized to a Gaussian approximation of the posterior, but we show that it won't be very necessary for the tasks that we're able to do with just the approximation with the Dirac delta. Also, another important thing that I'd like to mention here is that our conditioning. So I'm pretty sure that if you're familiar with the diffusion literature, you've seen that you can draw samples from the posterior by using classifier guidance, for instance, for which you need to basically have a classifier that can look at the intermediate noisy images and give you some guidance for every step of the sampling that you will be doing. But I'd like to point out here that instead, in our case, this conditioning is not applied to the intermediate noisy images, but it is applied on the final image. That's why it's a more attractive, let's say, term to call it plug and play. So even if I had a classifier, for example, I'll show this for faces, but if I had a classifier for facial attributes and I had just trained it on a bunch of noise-free images, I wouldn't be able to use it for this classifier guidance or whatever else they have been doing. Whereas for our method, we just want this to be able to just give us some signal for the final image. So we're able to use any external classifier without having to retrain on noisy images and so on. But I'll go this in detail when I mention it for the face experiments. So basically, what we want to point out here is that this constraint that we apply can be any differentiable constraint, and this is a very simplistic example. But for instance, if we just say that we want, for an MNIST DDPM model, if we just want thin or thick digits or asymmetrical digits, as long as the constraint is differentiable, we can apply it. And also, if we also train like a differentiable classifier, a neural network to give us classification of digits, then we can just apply that as a constraint. And as we saw here, we can use a classifier that basically detects the digit 3. So we say the conditioning is it being the digit 3, and any combination of those as well. And in general, pointing out this thing that I was mentioning before, the classifier and the constraint and whatever you want to think of only applies to the final image. So you don't need to change your classifier on the final images or sorry, on the intermediate images. And this is what the optimization procedure looks like. And you'll see that at the very first steps, this looks like a noisy image, and it's just because we initialize it with Gaussian noise. But the classifier or the conditioning is just trying to classify the final image. It's not trying to do anything with the intermediate steps, which is the main difference from other approaches. So here we show that we take a pre-trained diffusion model on FFHQ, and we take a face attribute classifier, which was trained on celeb A. And now we have the ability to generate faces with select attributes. So we start with some random noise, and we start optimizing this evidence lower bound. And basically, the classifier sets some condition, which is some attribute in the face, for example, blood or oval or eyeglasses, or any combination of those as well, like goatee and big nose. And by running this optimization process, we end up figuring out what the final sample should look like, such that it satisfies the classifier in this case, and also the diffusion prior. So it tries to satisfy both at the same time. And also here there's a small issue here, because the classifier, you can see this as sort of trying to figure out adversarial examples for the classifier. So since the classifiers are not perfect, they will be able to easily be fooled by some correctly placed noise in the image. And since the diffusion model is not perfect, it will allow for that noise. And we do found lots of these cases. For example, for the eyeglasses, it would be very easy to fool the classifier by just placing like a line on top of the nose of the face. But in general, we show that it's able to produce realistic samples. We just need to run also the final 200 steps of the diffusion so that we fix any sort of artifacts that we generate from this optimization process. And also, yeah, there's some work that's showing that you can do adversarial purification actually with Discord-based models, but this is not very related to our work.
So can I ask a question
yeah, sure.
regarding what you just explained? The slide before, actually.
Which one? This one or the previous one?
The one with the digits, with the missed digits. Yeah. So here you do this conditioning with a pre-trained classifier, right?
Yes.
Like so, a classifier guided generation, so speaking, and you use a classifier that classifies these attributes that you have there. So your classifier trained to classify thin, thick.
Oh, okay.
Symmetry, like how does it work?
No, so for the first four examples, the thin, thick, and asymmetrical digits, the conditioning is just, for example, for the thin digit, we penalize the constraint is penalizing the activations basically in the final layer. So it's saying that you should generate a digit that doesn't have a lot of values that are close to 1. So here we just show that whatever you can come up with as a differentiable constraint, we can use to generate samples that also satisfy the prior distribution. So here the thin, thick, and asymmetrical digits are just some handcrafted constraints that we put in on the final image. The learned constraint is the classifier for class 3, for instance.
Yeah, but it's not immediate to me how you go from thin to a differentiable constraint. See.
So a differentiable, if I remember correctly, the constraint for thin was to also try and minimize the final values of the. So you place a penalty on the final values of the image. So
okay,
this
so
is 0 to 1, so you penalize.
Yeah, like you basically have to come up with an actual constraint for a condition that you want to apply.
Yes.
So it's not like this is not like a text conditioned
classifier. No.
Classification. And the initial classifier that you're using is a classifier on a missed digit in this case.
Yes, exactly.
Okay. And another thing is you say that you need to apply the condition only on the last step. What does it mean? That you generate a full an image basically running, for example, 1,000 diffusion steps, apply the constraint, and then do 200 more?
So
or
you need to think of it as an optimization process. So you start with some random image, and you start optimizing it. You perform these gradient descent steps, and at each step you're trying to minimize the so you're trying to minimize the first term, which is the diffusion prior term. Basically, instead of doing it for every t at the same time. We just sample some t values, and we try to minimize for some t values. And you also try to minimize the condition, the penalty of the condition.
I see. So you don't train the model. Now the diffusion model is pre-trained, and you just optimize the condition on. So you start with noise, basically.
Yes, and we're optimizing the image with respect to the diffusion prior and the condition. So basically, we're doing gradient descent on the image pixels. We're not doing gradient descent on the weights of any model.
Yeah. Okay.
And the difference is, yes, so the classifier does not have to be applied to the intermediate steps, since we're only optimizing the final image. So we're saying that this thing over here is actually what we're optimizing, and you need to think of this as being x0 in every case. So the initial x0 is probably very bad and doesn't come from the distribution, but by applying these gradient descent steps, we make it more and more close to the prior and the condition.
Yeah, that makes sense. And then after you do the optimization, you run 200 steps of diffusion on the optimized image.
For the phases, yes. So we saw that after running the optimization, we get some artifacts because of the imperfections in the classifier and so on, and diffusion model. So just running some diffusion steps removes all the artifacts that we found in the images.
Yeah. Okay, now it's clear. Thanks.
Yeah. So this was for the phases, and this is what the generation process looks like. So you can see here that we don't have noisy images in between, right? The condition here, I think, is smiling female and blonde, if I remember correctly. So you don't have noisy images in between. You start with a noisy image because you have to initialize with something, but immediately you're trying to figure out what the final image looks like, and the conditioning only applies to the final image. So you'll see here that it's trying to draw eyeglasses, for instance, or it's trying to make the hair more blonde and so on. So these are not the intermediate steps of the diffusion process. If you look at the intermediate steps of the diffusion process, you probably have a lot of steps with noise and suddenly something appearing, like the low frequencies first and then the higher frequencies. So yeah, this is what basically the optimization process looks like. This gradient descent steps on the image. Now for a second example of an application, we show how we can actually use a diffusion prior to perform segmentation. And the task we wanted to solve was we have some land cover segmentation maps from some different areas of the US. And the problem there is that although the distribution of colors is very different because you have some images from Arizona and some images from New York, the underlying distribution of the segmentations is pretty much the same. The roads will always be straight. The rivers and the lakes will be connected. You will have forests in between, or you will have like barren land and so on. So the assumption here is that if we train a diffusion model on land cover segmentation maps and we're able to perform inference with that, then we won't be as dependent on the distribution of the colors as, let's say, if we trained CNN that looked at the images and tried to perform the segmentations. So in this case, we will use the diffusion model as a prior over segmentation maps. And the way we will use it is that given an image, we perform some color clustering of it. So basically, the color clustering gives you some local components, basically, that you need to paint with your diffusion model. And we also have some weak labels that we will be utilizing. And what we want to do is that we want to assign a class to each of the clusters locally, such that it looks like it comes from the distribution of segmentations that the diffusion model has seen. And I think that the final example is the most easiest to showcase that, where we have this image over here. We perform some clustering, and basically what we say is that I want you to assign a label to each cluster so that the neighboring clusters that have the same type of cluster should have the same label, and also you should be weakly following these weak labels that we have. And of course, the diffusion prior also applies that roads should be connected and you shouldn't be having water in the middle of the roads and so on. And we show that by applying this, we're basically able to generate segmentation maps for any kind of landscape. Whereas if you trained one model that looked at the images of the first landscape and tried to apply segmentations, you would have a huge domain shift, and then you won't be doing as well. And we use that to basically generate some examples of images and segmentations to fine-tune CNNs to do the job for us. So yeah, the assumption here is that the diffusion prior can be less prone to the changes in the distribution of the segmentations, which won't change as much, whereas the CNN that we will be training would have a real hard time at performing well at different locations. And this is what the results look like. And basically, the thing that we show here is that even if you train a model on a very huge CNN model that looks at the entirety of the United States, you probably don't do very well locally. So instead, if you have a model that knows what the distribution of the labels should be, you can just use it to sort of fine-tune your models and be able to do better locally instead of having to like get a huge data set and train on everything. But the idea is that we can use the diffusion prior as a prior over segmentations, and it doesn't really matter that the colors change that much. And now for one of the final example is another case where we want to solve a combinatorial problem by optimizing images. And let's assume that now we have some images X, but these X are some function of some latent variables. And I'll explain that in a moment for our case. So if we have a differentiable mapping between the latent variables and the images, then instead of optimizing with respect to the images, we can just optimize with respect to the latent variables. Since everything is differentiable, we can just backpropagate the gradients to the latent variables. And the example that we show is that we train a diffusion model on solved images of traveling salesman problems, and we use that to basically figure out the solution of the traveling salesman problem by just looking at the image. So to be more like clear, let's say that we have some adjacency matrix of the planar graph, and this is our latent Z. And now from this adjacency matrix, we can differentiably construct an image by just adding the edges present in the adjacency matrix with some appropriate weighting. So if we have an adjacency matrix with values from 0 to 1, then we can just paint the image basically differentiably by just adding the edges that are present in the adjacency matrix. And now what we're able to do with this is that if we train a diffusion model on solved TSP problems, then using our method, we can perform inference and generate samples from a posterior distribution, where our posterior here will be initializing with some vertices, and we will just be figuring out how to put the edges in between. And I mean, it's a bit weird at first. I understand that people don't solve TSP by looking at images of TSP problems, but we did find some work that showed that, for example, people can do a very good job at locally figuring out connections. So there's some inductive bias in the human visual system that shows that you can indeed locally figure out how you should be connecting these graphs. And also one important thing is that if you were to use, let's say, a transformer on the vertices, you would be scaling very badly with a number of vertices. So we don't see as much of that problem in our case, where we can just add more numbers and we'll just have the same size image basically in the output. So this is what the process looks like in that case. So you initialize with some random adjacency matrix, and you start optimizing the adjacency matrix in this case, such that it satisfies the diffusion model prior. So the diffusion model has seen 1 million solutions of TSP problems in the image space. And basically what you're doing is that you're changing your adjacency matrix at every step, such that the image that you render out of it looks like an image that the diffusion model would produce. And you hope that the diffusion model just produces the Tour images, the optimal Tour images. And again, this is what the process looks like as a snapshot. So you initialize with some locations of vertices, you start running this this optimization process on the diffusion, and initially it looks like it figures out the easiest cases, and then it does try to figure out like the tougher ones. One important thing here is that since you're not guaranteed to end up with like an exact tour of the graph, we also perform like a post-processing step to opt step. So we fix it up a little bit. But even with that, we're able to show that we can do as well as methods that actually look at the graph itself and try to solve the problem. And also here I'm showing that even if we add a lot more vertices, so for example, we trained this with 50, with the max number of 50 vertices in the input, but if we just drop 200 vertices in it, then we're able to actually try and figure out something. Probably it's not the optimal tour because the convolutional network is not trained with larger images, but it is able still to generate something that is plausible, and probably if you can add like some post-processing steps over it, you will be able to get something that is closer to the optimal thing. The important thing is that if you were to do this with by directly operating on the graph with some reinforcement learning algorithm, for instance, you will be struggling as you increase the number of vertices, because you would be scaling very badly instead of just looking at an image. So yeah, I think this was pretty much it. So what we wanted to do was to see if we can use these diffusion models basically as priors to do any other kind of task. So we don't want to just solve some, because people have been doing this again for inverse problems and so on. But we wanted to be as flexible as possible and show that whatever is the conditioning or the supervision, for example, that we have, we just want to use like these huge diffusion models that are trained on large amounts of data as a prior to perform any kind of downstream task. And we show that we can do an okay job at it for 3 very distinct tasks, I'd say, because I think that the strength here is that you can do lots of different things, and that's where we basically bet for this to be an important thing, because one of the problems was that previously with GANs, for instance, people just did conditional generation of images, but they didn't really use it as much for solving problems in the sense that we show here for segmentations and for combinatorial optimization. And obviously for future work, we're also looking at other problems that we would be able to solve with diffusion priors, such as language, where although it hasn't picked up yet, because people are not sold on using diffusion models for language, we have shown, we haven't published it yet, but we have shown that you can do a similar thing when you have a diffusion model over language and then a second like classifier that's trained maybe on different embeddings of words. And you can combine the two even though the embedding space is different. Yeah, I think that is all for me. Thank you very much for your attention, and I'd be happy to take questions. I think you may have some questions for the TSP because I didn't hear any.
Yeah, thank you. Thank you for the presentation. I can start with a question if it's okay. I was curious to know how much time does it take to do the optimization. So of course, I guess images and TSP and other things have different times, but
yeah.
Yeah.
So it's not a very fast process. One of the main drawbacks of this entire thing is that so here, when you're doing this optimization, you basically the biggest bottleneck is that you have to backpropagate through your denoiser network. So basically, when you're optimizing with respect to the parameters of the variational distribution, which in this case is just a point estimate, you have to backpropagate through this epsilon theta term, which is the most expensive part of this process. So for the inference for, let's say, a batch of samples that you can fit on your GPU may take for between 30 seconds to a minute, depending on which problem you're trying to solve. but the bottleneck is that you will need a lot of memory consumption because you're trying to backpropagate through this thing. And I understand that maybe for the models that we show, where you have some phase model or you have some segmentation model, these are not very huge. But if you were to do it for like stable diffusion or bigger diffusion models, this would be a real big problem.
And for a TSP, then okay, assuming that you have enough memory, right, on your computer for doing that, for a TSP, how long would it take to solve one specific problem?
Yeah, for this bit, I think it was in the order of 30 seconds for a batch of images. So it's an okay time, I guess, for solving one problem.
Yeah. And how suboptimal is the solution in TSPs?
So it's very close to the optimal. If you also add the heuristic, the 2-opt heuristic, then it gets I think close to 1% to the optimal solution for the problem sets that it has seen, which was comparable to other methods that did this with reinforcement learning, for instance. That was I don't know, that was what impressed me, to be honest. I didn't expect it to be that close, but I guess that deep learning is not very good at solving TSP.
Thanks. Case, please.
Yes, so continuing on the TSP problem, as you mentioned, the big advantage of this method is that the scaling to larger graphs is basically either if your image is big enough, just put more location on there, or increase your image size so you have enough space to put your nodes on the image, so you don't have this factorial scaling that happens. But I'm wondering, do you see a degradation in performance, or do you still see the same type of optimality when you scale up the problem?
Yeah, so there is a degradation in performance. For instance, here, if you look on this bottom right figure, basically we've trained the diffusion model on 64 by 64 images and some specific like size of the vertices and the edges and so on that we render. But if we take it to like double the size and more vertices and so on, you'll see that it has some biases to connect things locally. So you'll see that it's like forming some loops that don't make any sense, which are local and so on. So the idea here would be that if you were able to solve this like locally, for instance, if you split this into 4 images and solve each one locally, and then maybe you have a way to connect those local solutions to get like to an approximation of the final solution, it would still be a faster thing to do than like trying to solve everything with reinforcement, trying to solve everything with reinforcement learning. So yeah, there's a degradation in performance, but I think the impressive thing is that it even works by doing this way.
All right, thank you. That makes sense.
I have another question. You mentioned in the beginning the fact that the people from the inverse problem literature didn't like the flag and play name, right?
Yeah.
But indeed, I guess diffusion model can be used as priors in the inverse problems literature, also in the sense of plug and play as they tend to use it. So do you know of other works that have done this, or do you know if this approach can be used in that scenario?
Yeah. So I will not say this with 100% certainty, but if you have a linear inverse problem, then there is, I think, a closed form solution for this core-based model. So I do remember seeing works on medical imaging, for instance, MRIs, and so on, that show that you can use the diffusion models as a prior to solve these inverse problems. But the whole thing we're trying to do here is that we're not trying to constrain ourselves to this kind of literature, because I do understand that it is a very specific thing, inverse problems, and I don't want to be crossing into their literature, basically. So I want to sell this more like a general way of using a diffusion model as a prior, not just for inverse problem solving. But yeah, you'll see, I'm not sure if you've seen, but there's been some follow-up works from other groups that also try to do the same thing, where basically you will have your diffusion model that, for instance, during fusion, where you use your diffusion model on images to basically supervise your 3D NERF model or whatever you're training to generate a 3D scene. And in those cases, they do something very similar to this. You're trying to optimize for example, in this TSP problem, you have some latents that are your rendering function or whatever you optimize. But they do some things differently. One thing that people have figured out, but we're not so sure if it's good enough yet, is that how you don't backpropagate through the diffusion model when doing this process, because as it gets bigger, it gets more difficult to backpropagate through.
Thanks. Are there any more questions from anyone? Okay, then yeah, and thank you again for your talk. I will stop the recording now.